Very good. Well, welcome Stockholm, and welcome to those of you here in Durham. I want to do a couple of things, and then you may have some things you want me to do, or we want to do collectively. I want to talk a little bit more about the homework, and then if you've been following the email traffic, we had multiple questions via email following up on some of the conversation from the last class, and I want to talk a little bit about that too. But before I start with either of those, any other topics or questions that anyone might have? KTH, do you have any other burning questions beyond the ones already asked? It's a 5-second delay, right?
Thank you.
I think that means no, right?
Probably.
Yeah, probably. What about here around the table? Anyone have a question? No, everyone's happy momentarily. Let me talk about the homework. In the homework, you're being asked to use Hamilton's principle and or Lagrange's equation to drive the equation of motion. You should get the same answer. If you don't, keep working until they agree. And that equation of motion will have some coefficients which depend on the properties of the system, like the spring constant, like the flow velocity or the dynamic pressure, like the moment of inertia, the mass moment of inertia, and so forth. When you finally get that equation, I'm going to write it down for you. How about that? That's it. But I'm going to write it in an incomplete form, right? So there'll be something left for you to do. But once you have that equation of motion, you can, and often it's of considerable interest, to write the equation in non-dimensional form, because that usually is the most compact way to write the equation, but it also probably gives you greater physical and perhaps mathematical insight into what the equation means. So the equation, I just happen to have it with me, the equation of motion for the homework is homework number 1. It looks like this. It's in terms, of course, of that angle, right? The angle of twist of the spring. And it goes like this. It's alpha double dot plus omega alpha squared times 1 minus the dynamic pressure. Remember, the dynamic pressure is 1/2 rho u infinity squared divided by the divergence dynamic pressure equal to, I'll put a sub-infinity on here so you'll know I'm talking about the free stream. That same ratio of Q infinity over Q divergence times omega alpha squared times alpha. Now, what I've not told you, but you're going to find out, you're going to determine what omega alpha is, and you're also, of course, going to determine what Q divergence is, right? I'll let you do that part. So let me talk a little bit more about what this equation tells you. Of course, you can solve this equation several different ways. One way I suggested in the homework was to assume that Q, which in general is a function of time, is some, I'll call it Q bar, which doesn't depend on time, times the exponential to the lambda t. This is, what kind of equation is it? It's a differential equation, but more particularly, it's what kind of differential equation? It's a, what kind of words can we use to describe it? It's second order. Yeah, because the dots, I should have said this. Q dot, of course, means dq dt, and Q double dot means the second derivative of Q with respect to time, right? So it's second order because the highest derivative is second order. That's a good thing. What else is it? Any other words you'd like to use to describe it?
It's an ODE.
I'm sorry?
An ordinary differential equation?
Oh, it's an ordinary differential equation as opposed to a partial differential equation. That's absolutely true. Because it only depends on one variable, namely time. Later on, we'll have some differential equations which depend on both space and time, right? That will become a partial differential equation. But this is ordinary. That's good. I'm looking for one more word. So it's second order. It's an ordinary differential equation. And there's one other important characteristic that we often... What? It's constant also.
Linear.
Linear. Ah, it's linear. Oh, God. I thought we'd never get there. Linear. Most mathematical models in engineering science are linear in practice because they're a lot easier to solve. They're also somewhat useful. They also have limitations. There are lots of things that linear equations don't describe. So the research frontier in aeroelasticity and a lot of other fields is dealing with nonlinear equations. But if you go to Boeing or Airbus or any other aerospace company, is that true? Mostly you're using linear equations because they're a lot easier to solve. They're quicker to solve. And most of the time they give us a close enough approximation to what we want that we're happy. Okay? Okay, so this assumption is actually the most general form of the solution for any linear ordinary differential equation. But of course, we still have to determine lambda and have to determine q bar. And if it's a second order equations, how many lambdas will there turn out to be? How many?
If it's what?
If it's a second order differential, it's a second order, a linear ordinary differential equation. So how many lambdas will there be? 2. And for fourth order, there would be 4. And so second order is easier than fourth order because there are fewer lambdas to find. And, okay, but now there's another way you could solve this equation. You can run over to MATLAB and say, I have an ordinary differential equation. Here are the coefficients. Here are some initial conditions. Run out a time history for me because they'll have a piece of software that'll do that for you, right? So you can do that too. In this case, it's simple enough because it's second order and it's linear and all that good stuff. So if you make this assumption, you can work out the solution in analytical form. Normally, you can't do that, right, for real aeroelasticity systems because you may have a system of 10 or 20 or 30 ordinary differential equations which are coupled with each other. I mean, you're really doing this in an industrial setting. You'll have a lot of equations, so you'll have some computer codes. You will go to MATLAB or something, Fortran, whatever your favorite computer language is. Okay, what else I want to tell you about this? This tells you right away. Oh, thank you. This tells you right away that if Q infinity over Q divergence is 0, or really just small, right? Then you can certainly ignore that term compared to 1, right? You'll agree with that. So I'll give this equation a number. So now let's look at 1 under this condition, or let me not make it exactly 0. I'll just make it small. So when it's small, I'm going to ignore this term, right? Then I'll have alpha double dot plus omega alpha squared. Oh, I forgot to put an alpha here. That's important. Alpha, and this is alpha naught, by the way. Sorry about that. So that's alpha naught, and there's an alpha here. Plus alpha equals Q infinity over Q divergence, omega alpha squared, alpha naught. By the way, remember what alpha naught is? Oh, you're going to ask me what alpha naught was? Yeah. Oh, fine. Alpha naught is the following. And let me draw a picture. Remember, we have a spring connected to the airfoil, and let's think for the moment that it starts out in a horizontal fashion, and here's the flow coming in. If it's exactly here, then both alpha naught and alpha are 0, okay? But now I want to distinguish between the case of the orientation of this airfoil relative to the oncoming flow and the orientation which corresponds to 0 twist of the spring, because those don't need to be the same thing, right? I could build my system so that initially there's an angle relative to the flow, but the spring is not yet twisted. That's alpha naught. And then if there's twist of the spring, the total alpha of this plate relative to the oncoming string is alpha, the twist of the spring, plus the original alpha naught, which was just the orientation I made. And that's true in a real airplane, right? I mean, when it flexes, I mean, there's a rigid body attitude or angle of attack relative to the flow, but then when the thing deforms, there's some additional angle of attack because of the deformation. And in this simple model, we're just distinguishing between the angle corresponding to the spring twist and the angle corresponding to the orientation with respect to the oncoming flow. Kevin?
If we ignore Q infinity over Q divergence on the left-hand side, can or should we ignore on the right-hand side? Should we set the right-hand side?
Well, you got to be careful. I can throw away things if they're small compared to something else.
Yeah.
So I can throw this away if it's small compared to 1 and be confident that's a pretty good approximation. If I set Q, and that's why I made this almost 0, but not quite. If I set Q infinity over Q 0 equal to 0, I'm throwing away more than I want to because I do want to account for the fact that there is an alpha naught, right? So you have to make a judgment sometimes when you have equations as to what you keep and what you throw away. It depends on what you're after. So let's talk about that. If I throw away the right-hand side entirely, what do I have left? Well, first of all, I've thrown away the aerodynamics, right? If I set the dynamic pressure of the flow equal to 0, there's no aerodynamic force, right, in this model. So now I've got this oscillating in a vacuum. It is an oscillation, right? This is a spring mass oscillator. That's what that is. By the way, and what is omega alpha physically? It's the, what do we call that? It's a frequency. It's the natural frequency of the system, right? It's a frequency at which this naturally wants to oscillate. And mathematically, if I throw away the right-hand side and I solve that equation, it's just going to be an oscillation in time with a frequency omega alpha, right? Okay. But now, if I put the aerodynamics in, if I just put this term in, then the aerodynamics are forcing this spring mass system, right? If I include this term, not only is it forcing, but it's also changing the inherent dynamics of the system. There's something on the left-hand side, which is sort of a self-excitation due to the flow. There's something on the right side, which is, if you will, is an external excitation. In fact, if you just look at this equation, right, what does this term do? It modifies this frequency. It's no longer the same old in vacuum natural frequency. It's a new natural frequency multiplied by that coefficient. And by the way, if Q infinity over Q divergence is greater than 1, meaning Q infinity is greater than Q divergence, what happens to this term? Well, the frequency squared becomes negative. That's exciting, right? When you work it out, if you don't know it already, that means the system's become unstable. So this is the way you know that there's some instability. In fact, you can say, well, of course, you still have to find out what Q divergence is, right? But I'm not going to do that for you. That's helping you too much. Okay, so I just wanted to comment on the homework problem and point out there's quite a bit in that if you care to pursue it. Any questions about the homework? Okay, now you know what omega alpha is. Oh, you don't really know what it is. I mean, you know what the physical oh, no, you were asking about alpha naught. Now you know what alpha naught is, but you also know what omega alpha is. Any questions in Stockholm?
I have a question about the homework.
Okay.
It is asking to plot the frequency as a function of Q infinite.
Yes.
Yeah, but in the frequency we have a change from imaginary to real on certain value.
Yes?
So shall we make two different plots, one for imaginary and another for real?
Yeah, I would. Yeah, I would plot both the real part and the imaginary part for the frequency. Now, you realize that in this simple model, it's either going to be one or the other, but not both. But in more complex models, all the frequencies will be complex with both a real part and an imaginary part, right? And so when you do flutter analysis, at least one way you do flutter analysis, you will plot both the real and the imaginary part of the frequencies of functions, say flow velocity or dynamic pressure, and you'll see what happens at certain magic values of flow velocity. And again, they're in this problem that we're talking about, there are at least two frequencies of interest. There's omega alpha, which is the natural frequency, the in vacuum natural frequency when the aerodynamics are not acting. But when the aerodynamics are acting, then it modifies it, and there's now a new frequency, right? And as you point out, if you just look at this term, this coefficient in this simple model, you can rarely see when it changes sign. It changes sign Q divergence. Of course, you don't know what the Q divergence is, but I'm sure you can figure that out. Okay, so does that help?
Thank you.
You're welcome. Okay, let's talk about one of the questions that we had via email. And let me remember what that was. Oh yeah, yeah. This was we had a back and forth, which was, I thought, helpful. Hopefully not too confusing, maybe even enlightening. And the student was asking a question, had a couple of figures. I think he called them figures A and B. He had one figure like this. And he showed a compressive inload, which I think was called B. This was what he called figure A. And then another figure that looked like this. And I'm going to draw his picture a little differently. The solid line is what happens when there's no deformation. And I'm thinking of this, by the way, as being an elastic beam. And this is also an elastic beam. It's just, in this case, it's pinned at both ends. In this case, it's clamped at one end and free at the other, right? Well, if you, let's first of all look at figure A, which is not aeroelasticity, right? This is beam buckling theory. If I compress a beam and I compress it with a large enough load, I'll buckle the beam, right? It turns out determining the buckling load is an eigenvalue problem. It's a static instability where very crudely the P is playing the role of the aerodynamic forces in aeroelasticity. Or if you prefer, divergence is the aeroelastic equivalent of buckling, and the aerodynamic forces are playing very crudely speaking, the equivalence of this compressive load. Anyway, if you compress this and you hit the critical value of the compressive load, it will buckle. And it turns out it buckles into a shape like this. Actually, that's a half sine wave, but I could draw it a little better. Now, will it buckle up or will it buckle down? What?
Depends on the bias.
Depends on the bias. If it's a perfectly straight beam, according to the mathematical model, it's a random event as to whether it buckles up or buckles down. But if it's slightly bent, and it's slightly bent up, it'll buckle up, and if it's slightly bent down, it'll buckle down. Okay. But in the idealized straight beam model, it could do either one. Okay. Now, it turns out, by the way, if I had a cantilever beam and I press on it this way, it'll still buckle, provided when I do both the mathematical model and also the experiment, I'm very careful to keep the force P in the horizontal direction. I don't allow it to change direction, right? That's sort of the classical buckling problem. There's a different problem, which is the following. Now I let this deform in some way. If I assume that this force follows the deformation so that this is always aligned with the local slope, this will not undergo a static instability. It, in fact, will undergo what an aeroelastician would call flutter. This is the so-called follower force problem. And when people in mechanics who didn't really understand fluids were interested in, they exhausted everything you can say about buckling probably a long time ago. I mean, there's still some things you can say, but it's a well worked on topic. So they were looking for something new to do, and so they started looking at follower force problems because they're more interesting, because they have dynamic instabilities rather than static ones. Okay. And then there was a controversy as to whether it was physically possible to do this, that is, create a mechanism that would allow you to create a follower force. And there was a great controversy about this among notable people of the era, which is fun to read if you're interested in how human personality enters into science and engineering. Anyway, you can do this. In fact, we did an experiment like this. A guy named George Herman and his students worked for 10 or 20 years on this problem, both experimentally and theoretically. Okay, now, in the case of aeroelasticity, though, we're not interested so much, although we can include this effect too if we want to, but we're interested more in what happens when we have aerodynamics in the picture. Okay. So now let's think of, so this is what I'll call mechanical loading. Yeah, mechanical loading. But now let's look at what happens with aerodynamic loading. With aerodynamic loading, well, it depends on what the nature of the aerodynamics. So let me, first of all, treat a problem that is voluminously treated in the literature. In fact, a colleague wrote 2 books on this. And there have been hundreds, if not thousands, of papers written on it. In that case, often they do what they call the garden hose problem. There was a Brit who was an applied mathematician. The Brits like to do kinky things, at least some Brits. And so what they did was they had think of this as a pipe with there's a hole in the pipe, right? And the fluid flow can go through this pipe. So there's an internal flow with a certain infinity. And of course, you can do both pipes. You can do the cantilevered pipe as well as the pen-pen pipe. Guess what happens? In the pen-pen case, it diverges or buckles. In the cantilever case, it flutters. Okay. Isn't that interesting? Okay. Now, what about external flow? Well, it turns out if you have a long, slender body, the external flow problem and the internal flow problem are similar, except the coefficient, the numerical coefficient from the aerodynamic terms, is a little different. They're both of the same order. One might be pi and one might be 4 or something, but it's basically mathematically and physically, for that matter, the same problem. But then there's another problem which some of you might want to work on. I'm looking at some potentially guilty parties down at the end of the table. You could do the following case. Rather than this being a pipe, I think of it as a thin strip of aluminum, some metal, but it has some width. So from an aerodynamic point of view, it's more like a plate, right, rather than a beam. But structurally, it's like a beam because there's very little bending in the span-wise direction. All the bending is along the axis. And again, you can have a flow this way, or you can have a flow that way. Oh, thank you. It turns out if the flow is this way, it flutters. If the flow is that way, it diverges. And then if you think about, my friends in Stockholm can't see this, but you could orient the flow in all sorts of different directions, and you can see the transition as a function of orientation as to when it buckles or flutters. And so in recent years, we've done that and written a couple of papers. we're not ready to do this problem yet. Why not?
That's far enough.
It's harder than the ones we're talking about. That's why we're going to do the easy ones first. We do the easy, so it gets progressively harder as we go through the semester. And then in class, I discuss something, and then I assign a harder version of that for the homework. And that's the system, as you'll see, if you have not already found that out. Anyway, so we're not ready to do this because why? In order to describe this deformation, I'll call this deformation, let me draw a picture of the deformation. I'll call this deformation W, and I'll call position along this axis X. W is a function of X and T. Guess what kind of equation W satisfies? It satisfies a partial difference equation. And there's a linear version and there's a nonlinear version. The nonlinear version, which actually described this adequately, has only been developed in the last 3 or 4 years as part of our research activity here. People have solved the linear problem 20, 30 years ago, and then for the last so many years been trying to figure out what to do for the nonlinear problem. We finally think we have figured that out. By the way, when I say nonlinear, we're thinking about an equation for W, but there are really 2 equations. There's an equation for W which describes a structural deformation. There's a structural equation, but then there's an aerodynamic model that's required. And a controversy in the literature, which we think we've resolved, was the nonlinearity that's most important in the structural equation, which it turns out to be, or was it in the aerodynamic equation? Of course, if this thing bends enough, the aerodynamics will become nonlinear too, right? But the question is which one is more important, and that's often the subject of considerable concern. Okay, now I'm going to go on, but let me pause here because I've said all I want to say about this. Any questions? Not yet? Okay. Stockholm, any questions about this page before I move on to something else?
I just missed the part about the last diagram in aerodynamic loading where you said if the flow is towards the right, then it's divergence, and if it's towards the left, it should be flutter. I just missed the part of that.
Okay, what's the question?
Could you just repeat that particular part of it, where the flow direction is towards the left or right?
Oh, okay, fine. Yeah. In this diagram, is this the one we're talking about?
Yeah.
Okay. If the flow is this way, it will flutter. If the flow is that way, it will diverge. Now, there's no reason. I'm just telling you that because it's true. I mean, I'm not saying you should know that unless I'm asking you to take my word as a scholar and a gentleman that that's true. I mean, to prove that, you have to do quite a bit of mathematics, right? But since this subject came up, I thought I would share that little tidbit with you, that preview of coming attractions. We're actually going to do this problem later on, or at least some versions of it. But we're not, at least I'm not quite ready to share all those gory details with you. Does that help?
Yeah, thank you.
You're welcome. Okay, now let's go on, because there's yet another case that I want to draw to your attention. So let's look at this case. That's a wall of my wind tunnel, for example, or it's the fuselage of an airplane. And here's a wing, and I'm looking down on top of it. So this is a top view, if you will. Okay? And the flow is this way. If I look at this from the side, side view, then it just looks pretty boring, right? It's just this. right? Although, here's the ceiling. If you will, this is the side wall. This is the ceiling. And of course, there's a floor. And this, this is just the edge on view. Now, in our homework problem and our discussion up to this point, we have been looking at deformations of this, where there's an axis about which things rotate, right? So, if I assume that this motion in this view is just simple rotation, then if this is an elastic material of some sort, aluminum, steel, whatever, then fixing this wing at this point is equivalent to creating a spring. And that's why I looked at that spring model. But we can do better than that. We certainly want to do better than that when we're really doing it for pay, right? For some fine aerospace organization. And the way we do better is the following. Rather than using this representation of, using this representation of the spring to model the elasticity, we use what is sometimes called a torsional rod representation, where we have 1/2 now the integral from 0 to L of GJ. Let's see. I've already written partial. I'll make it a partial of alpha with respect to y squared dy. Right? I could write down the kinetic energy, which is 1/2 integral from 0 to L of the moment of inertia times alpha dot squared dy. And then I could write down the virtual work done by the aerodynamic moment, which is the integral from 0 to L of m sub y del alpha dy. Okay. Now, I have to be a little careful here because this I alpha isn't quite the same as when we were doing this model, because this is the I alpha per unit span. It's the distribution of moment inertia along the span. So it's the usual units of I alpha per unit length, right? And this is now the moment per unit length, too, along the span, the aerodynamic moment per unit. GJ is the torsional stiffness of this wing or this piece of metal. For those of you who don't remember what that looks like, let me point out to you what G is. Well, someone check me on this who remembers strength of materials. I think it's E over 2 times 1 plus nu, where this is the usual modulus of elasticity, and this is Poisson's ratio, right? And J, if this is a simple, if I blow this up a bit, it's thin, but it's not that thin. It has a certain thickness, which I'll call H, and there's a certain chord, which I'll call C, right? Then J is 1/3 CHQ. You knew that, right? If you don't know that, you can look it up in your strength of material book. So ask your friend who's a structural engineer or something like that. Anyway, these are characteristics of the material which give a representation of its stiffness. It depends on the material constants and also depends on the geometry, right? If this is thicker, it's stiffer. Okay? If it's shorter, it's not as stiff, right? And so forth. If it's thinner, it's not as stiff. And m sub y, we can still use our old model if you want to. It could be L times E, but now this is also L per unit span, so L would be Q infinity times C times, well, it's a low speed flow, 2 pi right? Q has the dimensions of pressure. So if I multiply pressure by length, I get force per unit length, right? To make it force, I have to have the length squared. So you could use this model, and you would come up with something that looks remarkably like the spring model, but a little more elaborate. And what would you do? You could use Hamilton's principle to derive the equation for alpha. And what kind of equation would it be? Do you think? Would it be linear? Why would it be linear? I agree with you, it would be linear. Why would it be linear? We're not sure. It would prove to be linear. The way you can tell is if it's quadratic in the energies, it's going to be linear when you get the differential equation. If this had cubic or quartic or higher order terms in energies, it would turn out to be nonlinear. So you can anticipate whether it's going to be linear or not. And here again in virtual work, it's the same thing. This is really quadratic, right? Because there's a del alpha here, but there's also an alpha in m sub y. So it's quadratic in that sense too, although one of them is a real alpha and one of them is a virtual or imagined alpha. Kevin?
Does that allow for alpha to change?
Absolutely. Yeah. But if alpha changes over the span of the wing, and I'll call this axis y, if alpha is a function of y, that's also a function of time, t, then what kind of equation will alpha satisfy? Partial differential equation, not ordinary. Yes, sir.
The integrand, is that small l, like a differential l?
Which L? The L in the limit?
Yeah.
No, I'm sorry, I should have said what that is. It's just the length of the wing. It's the span of the wing. Okay. Oh, I'm sorry. Thank you. It's the span of the wing. Okay. So if you want to determine this partial differential equation that alpha satisfies, you could use Newton's second law, but I wouldn't recommend. And no sensible aeroelastician would use Newton's second law. But if you use Hamilton's principle, once you master that and feel comfortable with that, it'll produce it fairly readily. And Hamilton's principle not only produce the equation of motion at no extra charge, it will produce the boundary conditions. It will produce the conditions here and here, because it's a partial differential equation, right? So we'll need boundary conditions at the two boundaries of the domain, at the two ends of the wing. Now the boundary condition here, I think is pretty clear. If I really clamp it here, then alpha is 0, right? Forevermore, at all times. And you may or may not know what the boundary condition is here. If you do, that's great. If you don't, not to worry. Hamilton will tell you if you follow his guidance. Okay. And so, guess what? You're going to have a homework problem that involves that, right? But since you're already working on one homework, I won't press you on that. The one thing I will say, one more thing about this. How are we doing? Oh, yeah, we got lots of time. Well, let me pause here because this is sort of a logical pause point and ask for any questions. But the next thing I'm going to do is, there's probably somebody in the group who doesn't really like Hamilton's principle. Can't imagine who that would be, but I won't ask for names. But if you want to convert this into an ordinary differential equation, right? I'll tell you how to do that. Right? And the truth to tell, the only way we actually solve PDEs is at some point we convert them into ordinary differential equations. I mean, there are various schemes for doing it. And there's finite difference, there's finite element, there's modal series, which is what we're going to talk about, because that's the way real aeroelasticians do it. Yeah. So, but nevertheless, it's of some interest, I think, well, I'll explain why in a moment. It's of some interest to know what the real boundary conditions are. And Hamilton will do that. Lagrange, unfortunately, will not. Any questions, Stockholm, before I go on?
Yes, I have a question about your equation of a movement. I think for that equation, I think we should use an S, like the surface area of the wing instead of the chord length. Is that true?
This integral is along the span.
Yes.
Any question?
Yes.
Yes, this is what I'm saying, you know?
No. I mean, the equation, is L equals Q infinity C 2 pi alpha.
Yeah.
The bottom one. I think the C here should be surface area, not the chord length.
No, it's a chord.
Why is it the chord length?
Well, because that's what the aerodynamicists in my group told me it was the right answer. Let me, since you asked, sometimes people may regret they asked, right? Well, not really. Since you asked, I will spend a few moments giving you a preview of aerodynamic theory. How's that? And explain where this comes from. But let me say this, and this may make you feel a little better. This model, this aerodynamic model, is not the ultimate truth. All models are an approximation of realities, but some are more approximate than others. This one is highly approximate. The next level of improvement beyond this is to recognize the following. In this equation, you see this equation that relates lift to alpha. Alpha, of course, may depend on y and t, and therefore, obviously, L does too, right? But in reality, what happens, the lift at one location y, at some position y along the span, depends on the twist at all other locations. It doesn't depend solely on the alpha at the same location at which I measured the lift. There's what is called an aerodynamic induction effect. That is, the twist over here changes the lift over here. This model does not allow for that. Okay? So that's one thing. Another thing is, an even better approximation is not to represent this in terms of moment and alpha, but to represent it in the following way. Del W, I'm sorry, thank you. Del W in C is really the integral over the area of the wing, dx, dy. Let me go back here so you know where x is. X is in this direction. X is in the flow direction, right? Of the pressure, the aerodynamic pressure, that's force per unit area, right? Times the deflection, that's a small w, not to be confused with capital W, okay? dx dy, right? Because P times dx dy is the force on a little elemental area, dx dy, and that's multiplied by the virtual change in the deflection, right, is equal to the virtual work. Now, how does this deflection W relate back to alpha, right? Well, let me draw you the picture again. Here's I'm drawing you a side view, right? And X is going in this way, and this distance I'll call suggestively XEA, where I'm thinking of EA meaning elastic axis, right? It's the axis about which this rotation takes place. And so what is the deflection? Well, the deflection at this point, because that's the point about which I'm rotating, is always 0. So I readily know that x minus xEA probably should appear, right? Also, I know that W is linear in x, right? And then what about alpha? There's an alpha out here, right? And if x is positive, if x is greater than xEA, then W has what sign? What is it, plus or minus? Huh? Was down, it's minus, right? If I take W as, if W is positive up, which I usually like to think, then when x is greater than xEA, W is negative, so I need a minus sign out front. So at some point in the future, not today, we're going to use this representation. Okay, we're going to use this representation. And because for some wings there isn't even an elastic axis. W, in general, W, well, you see it here. Alpha, remember, depends on y and t, right? So W, this small w, depends on y and t, but clearly it also depends on x. So I can use Hamilton's principle to derive a partial differential equation for W. And now it's going to be a partial differential equation to x, y, and t. Yeah. And then I can have any kind of wing I want. I can have a delta wing. I can, anything I like, really. But I will then require an aerodynamic model which tells me what the pressure is. And in general, it will turn out that the pressure at any point on the wing depends on the deformation at all other points on the wing. I mean, that's the kind of model that Boeing and Airbus and other fine organizations really use. But we're not ready to do that yet. At least I'm not ready to do that yet. Does that help you at all?
Okay, thank you. And I think I forgot the lift forces per unit span. Is it true?
That's true.
Okay, thank you.
You're welcome. You're welcome. Okay. So, again, now let me turn to something else. And again, we'll go back to the alpha business now. Return to alpha. Remember, alpha depends on y and t. But I can represent alpha in several different ways. But probably the most useful way is the following. I'm going to write it as some function of time, which most of the literature calls small q. Q1 of t times some function of y. And if I'm lucky, that's enough. But to be absolutely sure, I might want to allow for the fact there could be a second q and a second function. And then, of course, the more general form is sum over n of q sub n of t psi n of y. This is usually called a modal series, where these are the modes. Now, where do those modes come from? Oh, might not. Oh, yeah. Where do those modes come from? Well, divine insight, a finite element code. They come from looking at a simpler structural model than the one of real interest to me, but for which I can readily find them. But for the moment, let's assume I can find them. And we'll talk a little bit more later on about how to find them. If I do that, if I take this representation and I put it into expressions like u equals 1/2 integral from 0 to L, Gj, d alpha dy squared dy, and so forth, right? Also the kinetic energy, also the virtual work associated with the aerodynamic force. What will that do? Well, if I assume I know those functions from some reliable source, then I can work out all these integrals over y. And that will reduce the expression for u as the one entirely in terms of the parameters of the problem and the q's, right? So now the energies and the work are entirely in terms of functions of time, namely the q's. And that's what Lagrange needs to do his magic, or needs what we need to do to use Lagrange's magic, right? Yeah. Note that if we do this, and what's the advantage of doing this? Lots of advantages. One advantage is obviously you don't have to really think about Hamilton's principle any longer, right? If you don't want to. But another advantage is the following. What if Gj is not a constant with respect to y, right? In general, it could vary with y, right? In fact, in real wings, it does, right? Even if there's an elastic axis, the Gj is rarely constant. But once I assume this form, then whatever Gj is a function of y, if I know it, someone tells me what it is, then I can work out the integrals. And so all the complications of the y dependence go away, except I have to evaluate some integral. That's really nice. And if it turns out I only need one term in the series, then if you look at that solution on the final equation, I shouldn't say solution, but look at the equation of motion for just one term in a series like this, it will mathematically look just like our spring mass model, right? It'll look exactly, the coefficients will have a different interpretation, but the form of the difference equation will be the same. And you don't have to solve probably don't even have to solve the equation again if you've already solved the spring mass equation, because the form is virtually identical. Yeah. So that's what we're really going to do, or at some point in time. Okay. I think that's all I want to say today, unless you have some burning questions. Okay. Is that enough for one day to think about? What about you, Stockholm?
I have a question here, but maybe you are going to explain it later. Because in one of the videos, you explain a bit more about the different kind of boundary conditions we can have. But maybe you are planning to explain that later, because I would need to understand that a bit more. I mean, I didn't got it completely.
Okay. You're thinking about the different boundary conditions that one can have as a result of using Hamilton's principle? Is that
exactly that? Exactly.
All right. Well, at no extra charge, let's do that. As long as we have a little time. And so let's go back to our picture. Okay. And here's y. And it turns out that the boundary conditions all come from looking at, in this case, the potential energy. So I'm going to just deal with that. And we're going to use Hamilton's principle, right, to define the boundary conditions. And Hamilton's principle, let me remind you, is like this. It's del T minus del U plus del W, capital W, NC dt equals 0, right? All right, so the key is I need del U. And so by computing del U, I'm going to produce a term that I need for the equation of motion. But I will also produce the terms that tell me what the boundary conditions are. So let's compute del U. What is del U? Okay, well, here we are. I'll call this equation 1. What is del U? Well, I claim this is the following. Del U equals 1/2, still there, integral from 0 to L. We are not allowed to make virtual changes in physical parameters. The physical parameters are the physical parameters, all right? We're not allowed to make virtual changes in spatial coordinates. The only thing we're allowed to make virtual changes is something that represents deformation or motion of the system. So alpha is the only thing that undergoes a virtual change. So we have then Gj 2 d alpha dy times the virtual change in d alpha dy dy. Note that I've treated del as though it's the ordinary derivative operator. I mean, those are the rules. There's a whole mathematical theory that rationalizes this after the fact. I mean, Hamilton did his thing, and then actually Hamilton wasn't a mathematician, but he did his thing, and then for the next 100 years, mathematicians tried to give a more rigorous underpinning. So there are books on the calculus of variations. So if you want to know more about why we can politely do what we're doing, and has anyone taken a course in mathematics here at Duke that covers the calculus of variations? Anyone done that yet? No? Okay. There are whole books on just the calculus of variations. The best treatment is actually in a book by Hildebrand, which has a chapter, and it tells you everything you would want to know, I think. But there are much thicker books that tell you probably much more than you want to know. Okay, anyway, that's what we're doing. Now I'm going to use higher mathematics and cancel the 2's, right? That's always a good thing to do. And so what am I going to do here? Well, eventually I want to take all these terms and write them so that it's something times del alpha. Well, to make this del alpha, I've got to do something more, because I've got del of d alpha dy. But I can make it into del alpha by using one of the 3 or 4 tricks I know. And what trick is we going to use? We're going to integrate by parts. We're going to integrate parts. What did you say we're going to do?
I wanted to switch the derivative first. Bring the del inside, so it's just dy.
Oh, that would be illegal.
Is it?
Oh, yeah. Well, you could. I mean, oh, no, I'm sorry. You could do that. You could put the del inside here, so this is really d del alpha.
Yeah.
Yeah, I'll let you do that. But now a mathematician would worry about doing that. I mean, so if you get the big thick book, they'll spend at least a chapter justifying that. But yes, yeah, but it's all right. Okay. I'm sorry, I didn't know. But that's not enough. I need to do something more. And what do I need to do more? Integrate by parts. I'm glad you suggested that. So we're going to integrate by parts. Okay. And if I do that, then del U becomes the following. Let's see if I can. It's going to be Gj d alpha dy times del alpha at the end points. And there's a minus sign, right? Integral from 0 to L of the partial with respect to y of Gj d alpha dy del alpha dy. Oops. Thank you. So if you haven't integrated by parts recently, go back and look at your notes and verify that this is okay. Okay. So now I've got what I want, but if you like, I got more than I want. Actually, not more than I want. I want this too. So at some point, you're going to make the following kind of argument. You're going to require that everything that multiplies del alpha is under the integral sign. And by the way, there are going to be contributions from the kinetic energy and the virtual work, as well as this contribution from del U. Okay. So all those terms collectively will times del alpha. I'm going to argue that total coefficient of del alpha must be 0. Why? Because this is an imagined change in alpha. It can be anything I like, and if it can be anything I like, the only way the integral can be 0 and Hamilton's principle can be obeyed is if the coefficient itself is 0, right? Now, that's true formally, one would say that's true at all points for 0 plus to L minus, right? It's for all points in the interior of the wing. But right at the end of the wing, either del alpha must be 0 or its coefficient must be 0. At this point, when it's clamped, I can imagine any change I like, but it can't violate the physics of the system. If alpha truly is 0 at this point, then I can't make a virtual change, and I'm not allowed to do that. At this end, though, del alpha can be anything I like. Therefore, that term must be 0 at the end, which tells me that's the boundary condition, the one I was not probably immediately able to write down otherwise. Does that help, Stockholm?
Yes, thank you.
You're welcome. Okay. So now you're almost experts in Hamilton's principle and deriving boundary conditions. And we'll give you some more challenging cases later on to exercise your magic on, or Hamilton's magic on. Okay. I'm ready to declare victory for the day, unless there are questions. Are there any other questions?
I have one question.
Very good. I hope you have a wonderful day. Just remember that the basketball team is hurting badly and needs your support on Saturday. So I know you want to be working on your homework all the time. But for 2 hours on Saturday, you can watch the game and take a break. Okay? That's true for you too in Stockholm, by the way. We need your support as well.